So I'm going to make the life form smaller, and I'm going to change the number. So I'm going to add quite a few more gnats and a lot of mushrooms, and we can see what that does. So you see, it's pretty well scalable. You can create quite a few organisms. Let's go back and just really kind of push the boundaries here, see what we can get away with. So here we've got 500 gnats and 1,000 food objects, and frame rate is very, very slow, but you'll see that it's still chugging along here. Let's go back to defaults, and why don't we do this? Now there are some other organisms you can add into the simulation. So let's put some bats in there. Bats are going to be yellow. And some hawks too. Hawks are going to be red. And let's make them a little smaller since there's going to be so many organisms on the screen. There we go. Let's get rid of the labels, which are getting pretty high. So in this simulation here, the gnats, the green organisms, are still eating the statically placed blue food, but the yellow organisms are actually now eating the gnats, so they're chasing the green. They should be chasing the green ones. They're not yet, because their brains are random numbers, so they're just kind of circling randomly. The red hawks are eating the yellow bats, so we have kind of a linear food chain from red eats yellow, eats green, eats blue. And this is, running the same, just the same as the last simulation. Each population, or each species, is evolving independently of the other species. Independently, mathematically, in that the genetic algorithms are not connected, but obviously the fitness scores are very related, because whenever something gets eaten, it takes a pretty harsh hit to its fitness. Whenever something gets eaten, something must have eaten it. So they're definitely related values. We can see down here, all three species are being tracked in this panel, as their total fitness as well as their average fitness. And if we want, I'll wait till one more generation passes so the graph has a few more interesting points. But if we want, we can view a graph here. And similar to explaining the last graph, the dark green, the green lines represent the gnat species. The dark one is the maximum fitness, whereas the light green line is the average fitness of the whole population. You notice for yellow there's both a light yellow and a dark yellow line as well. And so if these values are just oscillating for now. Hopefully, if this ran for long enough, they would start to pick up. I can show an example of that later. So back to the setup, play with a few other things. So each of these species, the bats, I could actually load from a file some previously generated bat brains that have been exported from the simulation. And so I could do that for each animal species, so of which there are three, the bat, gnats, and hawks. Mushrooms don't have brains. They don't move. They just sit still. Look at a few other things. The generation time controls the number of frames it takes for a generation to pass. 2,000 is a pretty good value. It's actually a little low, but it's good for demonstration because we get some generations fast. I like to use, I think I was using 5,000 when I was doing the majority of my tests. Crossover chance is the chance that when you're creating a new generation, there's the chance that a mom and dad brain will randomly pick a point somewhere in their neurons inside of their neural network and just cross over to produce a child, so that a child will have something like 70% of the mother's brain and 30% of the father's. And it makes sure that those percentage comes from independent pieces of the brain to form the child. The mutation chance is just the chance that any weight in the neural network will mutate, and that's done for every child. Gets this run once, one pass, checking each weight, seeing if it should mutate, just randomly. And the max mutation is how much that weight is allowed to change, and the weights are all bounded between -1 and 1. So 0.3 is about a 15% change. Elite percent controls the percentage, I should say, of each generation which is allowed to be kept for the future generation unmodified. So the top 10% of each generation is actually kept and reseeded into the future generation without mutation or crossover. This is just because, if you stumble upon a great example while mutating, you don't want that example to be, do really well during the simulation, but then get mutated with all of its friends and crossed over with all the other performers in that generation, and you kind of lose it by the next generation. So if there ever is really a standout, you make sure that you keep that standout. Without this implemented in the genetic algorithm, you might see occasional sharp spikes in the max fitness where something great was stumbled upon, but then the very next generation you lost it. With this, you kind of ensure that a sharp spike, that guy gets kept, and you can hopefully stumble on and find an optimal solution faster. I'm not going to play with any of these for the simulation. It would take far too long to show on video, the effects. But this is controlling the actual structure and architecture of the neural networks, the number of hidden layers for computation, and the number of neurons per hidden layer. There are 5 inputs to every neural network, which are the polar coordinates of a vector toward the nearest prey, and the polar coordinates of a vector to the nearest predator, as well as the direction that the organism is currently looking, so that's 5. And the output is just how strong the organism should turn left or right, and that's kind of set in stone. That's hard-coded into the application. But the actual structure internally, the number of hidden layers, the number of neurons in each hidden layer is not, and you can alter that here. Here we're just evolving. We're not evolving by default the predator-prey action. We're really just evolving the prey, because we had 0 hawks, 0 bats, and just the gnats and mushrooms. We'll keep it 2040, I suppose. So let's take a look at some of the options to configure the food chain. This is the food chain editor. This shows our current setup with the mushrooms, the bats, gnats, and hawks. And we can look in the bat and see that he is chased by the hawks, the red guys. The bats are yellow, remember. And the bats chase the gnats. And, we can look in all of this and see all this information kind of spread out among the different areas here. If we want, we could say we don't want the gnat to have any predators anymore, so we want to remove the bat. And you'll notice that not only did that remove the gnat's predator, but it removed the bat's prey, which is the gnat. So, there's kind of a... For every entry down here at the 3rd level of this tree, there's a corresponding entry somewhere else. Similarly, if the gnats don't have the mushroom as prey, the mushrooms won't have the gnats as a predator. And that's kind of shown here. So, okay, we can also remove some of these basic life forms. So let's say we want to create a totally different simulation. Let's leave the mushroom for now. We can create our own life form. Let's call it, I don't know, a worm. And let's give it a color. So we'll say it's going to be magenta or some kind of violet. So we have the worm there. Let's also create I don't know, some other kind of food. We'll say chestnut. This has obviously no relation to real life here. This is not an animal, so it's just a food. So we'll see it's been added down here. And we'll say the worm eats both. Add some prey to the worm. We'll add the chestnut as prey, and we will add the mushroom as prey. So now we can see that both the chestnut and the mushroom are eaten by the worm. The worm eats both the chestnut and the mushroom. So everything looks good. When we hit OK, we'll return here, and we'll notice this configuration dialog has changed a little. We only have the worms to worry about now. There's no hawks, no bats, and no gnats as far as brains go. And let's create 20 of them. And let's create 20 chestnuts and 20 mushrooms. And now we can run the simulation, and we've seen that obviously the displayed organisms here have changed. And with regards to having 2 different kinds of food that one organism eats both, I mean, these food types could be identical. There's really no difference. But why don't we quickly try and set up a situation where it does matter. Worm, and what's another? We'll do blue jay, because it has a color in the title, so that makes it very easy to decide what color to use. So blue jay. Let's say the blue jay eats the chestnuts. That's nowhere near correct, but that's alright. So chestnuts. Ooh, let's say he eats worms too. How about that? This way we have some kind of relationship. And that actually is the first thing that may make sense. I think blue jays might eat worms. I don't know what blue jays eat. So here we are. Okie doke. Set them up. Run it out. Now we have, as you can see, the blue jays are eating worms. Oh, he just ate one. Yep. The blue jays are also eating chestnuts. And yeah, they're evolving. So I think that's pretty much it. I'll go back to setup screen. And yeah, so that's more or less it. I guess I'm going to show some video now of some fully... I took some video earlier after I had a simulation running for about 12 hours, which was a little bit too long. I mean, it didn't need to run quite that long, but I can show some graphs of the data, so let me just pull that up. So here's the simulation running after 936 generations. You can see, obviously, the gnats are pretty advanced. They're darting directly toward their prey, which is the mushrooms. And if we look at a graph of their fitness over time, you see that in this graph, the x-axis is the generations, and the y-axis is both the max fitness and the average fitness. The darker line shows the max fitness, the lighter line shows the average fitness. And you can see we kind of tread water for a while here at the beginning, random numbers, until some crucial point where a few gnats kind of stumbled upon a good neural network for a solution to the problem, and then you can see a period of refining where they, the genetic algorithm was actually doing some good work, until finally we hit a point where they kind of achieve some kind of peak fitness for, based on the number of food and the number of gnats, really when there is some kind of max fitness. And then since then they've just kind of been oscillating around at that max fitness right there. So look back at the graph for a few seconds. Yeah, that's pretty much it.